Good afternoon. I'm Pietra, and I'm a toolchain engineer at InBecosm. Together with my colleagues, Mary and Jessica, we will present our work on the Core 5 toolchain. So here we see all the components which make up a modern GNU toolchain. For standard RISC-V, we can already compile Ada, C, and C++ with future support to Fortran and OpenMP. We have the compiler, GCC, the GNU assembler, GAS, the GNU debugger, GDB, and a set of binary utilities. We also have low-level libraries to support C and C++ on any RISC-V variant, and also a range of standard C libraries for systems both large and small. We have the option to use a handwritten assembler or to use CJang to generate assembler, disassembler, and simulator from a semi-formal description. So let us look at supporting the Core 5 variants of RISC-V. These are all standard RISC-V cores, so we can use the standard assembler and compiler. However, Core 5 has a number of instruction set extensions which we wish to support as well. Our initial focus is to extend the compiler and assembler, which are highlighted in red, to support these instructions. For now, we are extending the handwritten assembler and disassembler, but in the future, we hope to extend CJang to give us automatic generation together with a simulator. This project has been running since the middle of August. Our approach is to, in turn, support the 6 groups of instruction extensions shown here. We shall provide support in the assembler and linker, followed by GCC built-in function support, and finally GCC optimization patterns to use these instructions automatically. To make it clear that the toolchain is targeting Core 5, we use the vendor field of the target triplet. Thus, we shall have RISC-V 32 Core 5 ELF instead of RISC-V 32 unknown ELF. We shall provide additional architecture specifications to specify either the whole Core 5 support or just selected parts. Finally, all Core 5 instructions will be prefixed by CV. The first commit to upgrade the assembler to support hardware loops was made last Friday and is downloadable as source from the Open Hardware Group GitHub, as well as a prepackaged binary from InBecosm. My colleague Mary Bennett will now demonstrate the new features.
Thank you, Pietra. A widely used function in GCC is memcopy. It takes a block of memory and transfers it to another place. Even if not explicitly used, GCC will still call it every time it needs to copy a struct. Therefore, an efficient implementation is necessary for high-performance computing. On the left of my screen is the disassembly of memcopy from the standard RISC-V nano-newlib standard library, optimized for code size. It is a simple loop with a counter register, A2, that decrements for every byte in turn that is transferred from the source pointer, A1, to the destination pointer, A0. I have rewritten this to use a hardware loop in the function myMemCopy, which you can see in the lower right-hand side of my screen. This function will be faster because it does not need to decrement a counter or branch explicitly. The code uses the RISC-V ABI and the correct assembler directives. Therefore, it can be linked into the code. You may notice that I use .option no RVC, which disables the compressed instructions. This is because the hardware loop instructions are incompatible with compressed and require the instructions to be uncompressed. .option push and .option pop are used to save and restore the options each side of the loop. For now, I have to assemble explicitly with these instructions, So the first command I use to assemble the Core 5 assembly code is this. I now need to test this function, which means I require a main program. As you can see on the upper right of my screen, there is demo.c. It has an array of 5 integers, initialized 1 through 5, and uses my memcopy to copy this to another array. I can compile this to an object file using GCC. Please note that I have not used the Xcore 5 extension. This is because it has not yet been added. Fortunately, the ABIs are compatible, so we can link it in. I drive the linker from GCC to create the executable. I can see this is good by looking at the disassembly and searching for my memcopy. All looks good. I have not run this on an FPGA board, so your exercise, if you choose to have an attempt, is to run this on your Nexus A7 board to see if you get the same output. But for this, you need the latest toolchain. My colleague Jessica will show you how to get that.
Thank you for the demonstration, Mary. If you wish to try using the new compiler, you can download a convenient pre-built binary from the Embecosm website. You'll find versions for all major operating systems, along with links to the source code, scripts to build the toolchain, and test results. We'd also encourage you to become developers. You can find out more via the open hardware group Mattermost Software GNU Tools channel. You can sign up to the open hardware software mailing list and attend our monthly meetings. And finally, we'd welcome your pull requests against the development code bases on GitHub. Thank you for listening. Mary, Pietra and I will be here for the rest of the afternoon, along with our colleagues Jeremy Bennett and Simon Cook, to answer any questions you may have.